Section 2.4 is on transformations of nonlinear equations into separable equations. And the method we're going to be using is called variation of parameters. So how does variation of parameters work? Well, we're going to be considering nonlinear, non-separable differential equations. And we're going to determine a specific function y1 that's going to be suitably chosen. And we're going to multiply it by another function u that will give us a function y that will satisfy our ODE. So we will have then transformed our non-separable nonlinear ODE into a separable ODE. A very specific type of nonlinear non-separable differential equation is called a Bernoulli equation. So a Bernoulli equation is given in the form y prime equals some function p of x times y, and it equals f of x times y raised to the power of r. So when we were looking before at linear first orders with y prime plus p of x, y equals f of x, we were able to use a linear integrating factor. But where this has changed is now we have a nonlinear ODE because of this y to the r term on the right-hand side. So this is a very specific kind of nonlinear, non-separable ODE. So this works for all values of r that are real, and I wrote out for you that that's what it means. That little upside down a means for all. So for all real r's, then other than 0 and 1, because if we let r be 0, then we would just be multiplying f of x times 1, and we're back to a linear first order, and we can do integrating factor. If we let r be 1, then we can combine p of x and f of x into being one function of x times the y's. So r has to be bigger than 1. It can't be 0, it can't be 1, it needs to be between them or bigger than 1. So we can transform our given ODE into a separable equation using variation of parameters. So I had mentioned that before. Well, how does this work? Well, the first thing that we're going to do is we're going to set our given ODE equal to 0, because we're going to solve for the complementary solution, which is what we call the solution to the homogeneous version of our ODE. So once we find a non-trivial solution to that homogeneous form of our given ODE, we can make that y1. So once we have a y1, we're going to let y equal u times that complementary solution. And then we can find the derivative of y prime through the product rule to be u prime y1 plus u y1 prime. And then what we'll do is we'll simply go back and substitute now in the y and the y prime that we just found in terms of u and y1 into our ODE as given, with the right non-homogeneous part included. And then we're going to find that we can reduce terms and we can move all of our variables to different sides, and we will now have a separable equation. Probably sounds a little bit like math magic, but it's actually a really cool process. So let's see how this works. I'm going to be covering examples 1 and 3 in this video because I already made a video on how to do example 2. So example 1 says solve the Bernoulli equation y prime plus y equals y squared. So our first step is to find complementary solution, meaning we're going to take our ODE and we're going to strip off the y squared and just set it as y prime plus y equals 0. So here we can just use the linear integrating factor. So with our linear integrating factor, mu of x is going to be e to the integral of p of x dx. Well, in front of y, I only have 1. So we're looking at e to the integral of dx, or just e to the x. So now when we multiply our ODE here by e to the x, we get e to the x y prime plus e to the x y equals 0. And in fact, this is the same as e to the x times y, the derivative of that product. So now, when we integrate, we find that we get e to the x y equals some constant. So y is equal to c e to the negative x. So this is our complementary solution. So this is what we're going to call y1. And step 2 of our process says, okay, now that you've found y1, you need to let y be u, which is a function of x, times y1. And then we know that y prime is going to be u prime y1 plus u y1 prime. So let's plug those back in. Well, here y1 is e to the x. Oh, sorry, c e to the negative x. We're going to go ahead and lose the c here because we're going to assume that it can be rolled into the u. So we're just going to say u e to the negative x. So to find y prime, we need u times negative e to the negative x plus u prime e to the negative x. In this case, we end up with, I'm going to switch the order around a little bit, make it u prime e to the negative x minus u e to the negative x. So now we have to plug these back in. So we need to plug back in y into both of these y's. And then we also need to plug in y prime into this y prime. So let's do that. So we end up with u prime e to the negative x minus u e to the negative x plus u e to the negative x, and it's going to equal u e to the negative x, the whole thing squared. So what happens is the negative u e to the negative x and the positive u e to the negative x are going to cancel out. So once these guys cancel out, we're left with u prime e to the negative x equals u e to the negative 2x. Properties of exponents, it's squared, you can bring it in. Oops, and that makes it u squared. I almost forgot. So now we can get all of our u's on the left and our x's on the right. So we can get du times u to the negative 2 is now going to be, well, that's e to the negative 2x times an e to the x dx. So we end up with, let's see here, u to the negative 2 du is going to be, well, I guess that's just e to the negative x dx. So that actually worked out pretty well. So let's integrate both sides and see what happens. So from here, the integral of u to the negative 2, add 1 to the power and divide, is going to be a negative u to the negative 1. And e to the negative x is going to be 1 over negative 1, so just negative e to the negative x plus c. Or negative 1 over u equals negative e to the negative x plus c. So in that case, if we run the negative through, u equals e to the negative x plus c. The sign of c doesn't matter, so it doesn't matter if you write plus or minus c. We're just going to leave it all as plus, and then if c ends up being a negative, it becomes a negative. So now we know what u is. It's e to the negative x plus c. Oops, sorry, 1 over u is. And so that tells us then that u is 1 over e to the negative x plus c. So now that we know that, our very last step then is to say, okay, then I know that y equals u times y1. Well, u is 1 over e to the negative x plus c, and y1, we just said, was e to the negative x. So we put our e to the negative x here. So we end up with e to the negative x over e to the negative x plus c. And if you do a little bit of moving around, the e to the negative x on the top, when we bring it down to the bottom, will become positive. So we'll end up with e to the positive x times e to the negative x, which is going to give us e to the 0, which is 1. So we end up finding out then here that y is equal to 1 over 1 plus c e to the x. So a little kooky on how we get there, but we can certainly find our y. As a reminder, I already have a video posted for this one. It's very, very similar to number 1. It is subtraction instead of addition, and there is an x in front of the y squared. That's the only difference. This last one is definitely not the same as the first two. So it's a little different, but we can make it work. So first of all, we need to put this equation in standard form. So right now, let's see here. If we multiply both sides by x, we get xy prime equals y plus x e to the negative y over x. So still not exactly what we're looking for. Let's move it around a little. Xy prime minus y equals x e to the negative y over x. So now if we divide everything by x, we get y prime minus 1 over x, y equals e to the negative y over x. So we got to change just a little. And that's going to be what we're looking for, because now we can use our variation of parameters. So let's start with step 1. Let's find the complementary solution, which means y prime minus 1 over x, y equals 0. And here, because we have linear first order, we can use the linear integrating factor. U of x is going to be e to the integral of negative 1 over x dx, or e to the negative natural log, the absolute value of x, which is going to be, as we've seen several times before, e to the natural log of the absolute value of x to the minus 1, which ends up being, in fact, x to the minus 1. So what we're going to do is multiply the entire equation by 1 over x. So 1 over x, y prime, minus 1 over x squared, y equals 0. And in fact, this is 1 over x times y's derivative, and it equals 0. So if we integrate both sides, we end up with 1 over x, y equals c, or y equals cx. So there's our y1. Our y1 is just going to be x. So as ugly as this one looks compared to the last one, the process is a little bit easier on this one, because now we're going to let y equal u, y1. In this case, then y is going to be u, x. And y prime then will be u prime x plus u by our product rule. So now when we plug it in, I'm going to plug it back in to this simplified version. So let's see what we've got. Y prime is u prime x plus u minus 1 over x times y. And y is ux. And it's going to equal e to the negative, well, y, which is ux, over x. Well, it looks like we're going to have some cancellations going on. These x's cancel, these x's cancel, And we're left with then u prime x plus u minus u equals e to the negative u. How about that? And those u's are going to cancel. So we're left with then, let me grab the right color. There we go. U prime x equals e to the negative u. If we move the e to the negative u to the other side, we get e to the u du equals 1 over x dx. So if we integrate both sides, we get e to the u equals the natural log of the absolute value of x plus c. So this one's going to be kind of an interesting one because to solve for u, you're going to have to take the natural log of both sides. So u is going to be the natural log of the natural log of the absolute value of x plus c. Which means then, in the end, since y is equal to ux, so we put up here y equals u times x, so y is going to be x times the natural log of the absolute value of x plus c. So I assigned you a few problems from this section to look at, and they are problems 3 and 19. So please check the homework set for homework 2 to see which ones you have to do.